Let's look at a similar but different rotational inertia problem. I believe this is the first time that I've noticed that the AP Physics C Mechanics exam has asked a non-uniform mass distribution on a rotational inertia problem. Might be the only time, but it could be that I just never noticed the other times. So this is 2018 Physics C Mechanics, question 3, and it's the very first part of the question. It says a triangular rod shown above, and I redrew their figure, has length L, mass capital M, and a non-uniform linear mass density given by the equation lambda equals 2m over L squared x, where x is the distance from one end of the rod. Using integral calculus, show that the rotational inertia of the rod about its left end is ml squared over 2. So we're asked to prove that this is true. So it's a similar situation, except that the mass distribution is no longer uniform. You just say that this is the x-axis, and that's the y-axis. Well, since this is our function for lambda, then if we integrate that, we ought to get the mass. So let's check that. The mass should equal the integral of lambda with respect to x. From here to here, we should get the total mass, which we were told the mass of the rod, or did they call it a rod? I did say rod, even though it's triangular shaped. That's going to equal that capital M. So let's integrate from 0 to L that function and check that. (2m) and L squared are all constants, so we're just integrating x dx from 0 to L. So then 2m over L squared times L squared over 2. That worked. We got the total mass that they told us the rod should be. Well, that means that this quantity, lambda dx, that must be equivalent to dm, because the total mass of the rod must equal the integral of the infinitesimals of the mass. So lambda dx is equal to dm, and that's equal to 2m over L squared x dx. Now we can integrate and find I about the end, because now we know what dm must equal. It must equal 2m over L squared x dx. So I is equal to the integral of r squared dm. It's always a good idea to start out by stating the basic equation, and that equals the integral 2m over L squared r and x. We should make those agree, so that will be x squared times x dx, where this dx and x are in the equation because that's what we found dm to be, and this x squared is in the equation because that's r squared. We just changed the variable to make them all agree. So again, 2m and L squared are constants, and we have the integral of x cubed dx from 0 to L, because this rod also has a length L, and that's just L to the 4th over 4. So we have 2m over L squared times L to the fourth over 4, and we've done it. That will be 1/2 ml squared, which is what the question asked us to prove. Thanks for watching, and remember, what one fool can understand, another can.